Hello, I'm Jacob. I'm going to be talking about genomic surveillance in the UK. Just to give a brief overview of what the talk is going to look like. I'm going to talk about my background and motivation. Then I'm going to talk about existing work in the field of surveillance, then what my project actually is, and then a bit about future work and impact and what this can lead to. So just to give some background. Pandemics are a major existential risk. Hopefully everyone is somewhat aware of that. We have engineered pandemics, which are probably the most likely X risk, and also natural pandemics that are less likely to present an existential risk, some might say, but definitely more tractable, so definitely worth discussing. Early detection of pandemics gives us a huge advantage in dealing with them. These things are exponentially growing, so they become significantly more difficult to deal with over time. So the earlier we can deal with them, the easier it is. And genomic surveillance is one tool that could be used for effective early detection of these potential pandemics. What we could do, we could spot it early, stop it spreading, rather than what currently happens, which is we only really detect things once they've already spread quite significantly. Spreading. So what actually is genomic surveillance? Genomic surveillance is tracking diseases in real time based on their genetic material. When I say real time, I just mean we're doing it quick enough that it can inform public health policy. And surveillance in this context is just looking out for diseases. It kind of doesn't have the same negative connotations that you would with like kind of CCTV and that kind of surveillance. It's a rapidly growing field. We've been kind of investigating diseases based on their genetics for quite a long time, but as sequencing has become cheaper and quicker, we've been able to do it much more easily. Ebola and SARS-CoV-2 are probably the two main examples of pandemics where it's been used, but it has also been used for lots of other smaller outbreaks and kind of other diseases. It is a really powerful tool for mitigating pandemics, and that is how it has been used generally. This has been, when there has been a pandemic happening, we can look at kind of how we can reduce the negative impact. It has been used less frequently in completely avoiding pandemics, which is what my project is about. So existing work in the field of surveillance, there have been quite a few past projects. Lots of this has been specific disease surveillance, where I kind of looked at one disease, tracked this, tried to reduce the impact. One example of this is wastewater surveillance for polio. This was used very successfully in Israel in 2013. They had what they call a silent polio epidemic, where they detected lots of cases and were able to immunize people and eradicate it before any cases of plastic paralysis occurred. So that was really successful. Another interesting one is dead bird surveillance, avian influenza virus, where in kind of poultry farms, they look for dead wild birds that are near it and then sequence them, detect any viruses that might be spreading in the bird population. These are just two random examples. I think they kind of showcase the different ways this can be used. USAID Predict was a really large-scale animal surveillance program where they took 130,000 samples from animals across 10 years, mostly focusing on Asia and Africa, where there's high human-animal contact. They detected lots of new illnesses, lots of new diseases, including 110 novel coronaviruses, but this didn't actually help much with dealing with SARS-CoV-2, which is quite an interesting point that I will come to later. And other than that, there have been lots of smaller studies which are quite useful for kind of finding methods and kind of ways of doing this, but none of them are kind of massive surveillance systems themselves. The other really interesting thing I came across was a future proposal for a nucleic acid observatory, which is one of the most significant pieces of work kind of in this genomic surveillance field. It's a major proposal for US biosecurity that involves mass environmental surveillance. We're taking daily or bi-weekly samples from wastewater at ports of entry to the country and also all hydrological basins. And in theory, this can detect everything that's contained within them, including any new pandemics, any pandemics that are re-emerging, any bioweapons. There is some debate as to whether it would actually work as described. I think in my opinion, it may well work, but I think slightly more work is needed to basically demonstrate this and to actually kind of see whether the techniques they're using would work as described. And then also there's a question of how does this apply to the UK? I think the UK has a couple of kind of quirks I'll come to in a second, which means this might not be the best approach to do here. So what's my work? My project was called Implementation of Genomic Surveillance in the UK for Detection and Avoidance of Future Pandemics. Nice catchy title. The key thing here is that I was focusing on the UK, partly because we have a really strong position to implement better biosecurity. We have a good centralized healthcare system. Our government is generally interested in this stuff. We have a quite small and densely populated landmass, and we also have quite high GDP because these systems are expensive. Also, I didn't want to repeat the work that had been done for the Nucleic Acid Observatory, but rather I wanted to kind of build on it and apply it to a different situation. We're also in quite a unique position for genomic surveillance specifically because we have really good existing sequencing strength. For example, the COVID Genomics Consortium is currently sequencing about 20,000 samples a week. This isn't a perfect comparison for surveillance because they're doing very, very targeted surveillance, which I will mention again later, but I think it just demonstrates the kind of strength that we have. As part of my project, I identified 3 options for surveillance that we could use. There's clinical surveillance, human-animal interface surveillance, and environmental surveillance. And I'm now going to go through each of those. So clinical surveillance just involves obtaining the genetic material that we're analyzing from clinical settings, hospitals, doctors' offices, that kind of thing. Obviously, this naturally targets the people who are likely to be ill rather than sequencing lots of healthy people, and therefore is highly efficient. But you're naturally going to miss anything asymptomatic, which could include any diseases with long incubation periods or any kind of engineered pandemics that are designed to be hard to detect. Just an example, HIV is thought to have been in circulation for about 60 years before we first detected it, just because it was so asymptomatic, and we needed kind of lots of symptomatic AIDS cases before we came across it. Clinical surveillance is currently used a lot in the UK to track influenza and influenza-like illnesses, ILIs, although this is done with non-genomic methods. So they look for symptoms that appear in GP offices, such as doctors, and they will get reported. And then we have some sentinel hospitals that do kind of more diagnostic testing. An expansion of this could be a really strong way of avoiding future pandemics. Obviously, it would only include influenza-like illnesses, but there's a good chance this would include lots of future pandemics. Influenza itself has caused, I think, 10 major pandemics in the past 300 years, and anything with kind of flu-like symptoms would be caught by this kind of surveillance. There's a good chance that had we had this in place before SARS-CoV-2 happened, we would have spotted it earlier than we did. So yeah, that's clinical surveillance. Human-animal interface surveillance is based on the theory that natural pandemics have a really high chance of arising at these human-animal interfaces, where there's lots of interaction between humans and animals, agriculture, wet markets, that kind of thing. The UK also has quite a lot of intensive animal agriculture here. There's a good chance of these diseases originating in the UK. Again, we're targeting the origins of the pandemics, which is quite efficient. Also, because we're targeting animals, there's a good chance we'll detect it, possibly before it even breaks through into humans. And obviously, earlier is always better. But again, key limitation, we're going to miss any non-zoonotic diseases. So that would include a small proportion of natural pandemics and any engineered pandemics, which is quite a major limitation. USAID Predict, I mentioned earlier, was a really large-scale example of this. And they did successfully predict that coronaviruses would pose a large risk. That didn't actually help us deal with SARS-CoV-2 very well, which raises kind of interesting questions as to why. It could just be that it was an underfunded program, and if it was bigger, it would have done it. I think it's more likely that it actually just shows an issue with policymaking, in that once we've detected these possibly concerning pathogens, what do we do next? Which is, I think, quite an important question that hasn't been answered. And then environmental surveillance is surveillance of sewage, wastewater, rivers, which contain material from everything within the watershed. Targeted environmental surveillance, like I mentioned earlier, in terms of specific diseases, has been used very successfully. Broad, untargeted metagenomic surveillance is probably what holds a lot more potential, because that can really detect anything. Metagenomic just means it's an environmental sample that contains lots of distinct organisms, and we then need to do kind of analysis to actually break down what's inside it. And because it's completely unbiased and untargeted, it can theoretically detect anything. But it does have sensitivity issues. It can be quite challenging to get quantitative data from it. It can sometimes suffer from low taxonomic resolution, which is distinguishing from closely related organisms. It's quite difficult to predict pathogenicity based on sequence. So once we've kind of got a sequence, how do we actually tell if that's a danger to us? It's also got some problems with read depth. Read depth is basically just a measure of how much sequencing we need to do to detect something. Because the organisms we're going to be looking for are probably at very low concentrations, it can be quite hard to find them by sequencing, and you do a lot of it. And because of all that, it can be really, really expensive. So the conclusions I reached was that we want a combination of all three. On the clinical side, I think we should be sequencing every hospitalization for influenza-like infections. This gives us a really strong chance of catching any influenza or influenza-like, or possibly just any respiratory infections, for relatively little cost. At peak flu season, we have about 1,200 cases, 2,000 cases, which isn't that many. It's quite doable. On the interface side, I think we could be doing a daily sample from every intensive farm in the UK, which gives us a really strong chance of catching any emerging zoonotic diseases. There are 1,674 farms, so that's 12,000 weekly samples. This could be wastewater surveillance on the farm or directly from animals. I don't have an answer which of those is better. And on the environmental side, I think a good pilot study is absolutely worth doing. This would probably look like a single city or a single watershed, just testing the efficacy and feasibility of this approach. Can we actually detect the things we want to detect? The UK is a lot smaller than the US, so it would probably be quite doable here. And then it could scale up to give full coverage, which would be 24 ports of entry and 35 hydrological basins for 500 weekly samples. This is 15,000 weekly samples in total. You might remember earlier, I mentioned currently sampling 20,000 samples a week for coronavirus. It's not a fair comparison, because this stuff is the metagenomics, which is much harder, and kind of untargeted, which is, again, takes longer. costs more compared to the very, very high throughput targeted coronavirus sampling. But I think it does demonstrate that 15,000 is kind of a vaguely realistic number. Also, this whole approach is highly adaptable. On the clinical side, you could expand it to include other indications beyond kind of influenza-like illnesses. On the animal interface side, you could just do more sampling and include smaller farms. And obviously, I've already mentioned how the environmental can scale up. To briefly touch on what my final deliverable is, I did it as a post-note style policy brief, which is what they use in the Parliamentary Office of Science and Technology, which is 4 pages of concise, accessible writing. Mine was actually 5 because of formatting, but same idea. I thought this would be most useful if policymakers or other people wanted to kind of pick up on this work. I also included some more technical appendices, just giving kind of better justification, a bit more quantitative detail, and yeah, just more detail. I also included more discussion on how each option could be done, so more discussion on kind of targeted versus metagenomic sequencing, which I just don't have time to discuss in the talk. To very quickly go through future work, I think this can loosely split into kind of more practical side, looking at implementation, and then also the more scientific and theoretical side. On the practical side, obviously the pilot study I mentioned could be done by a small company, a startup, if you're just basing it in one city, just to basically see if it works as a proof of concept, demonstrate that it's feasible. I think you would need government buy-in or NHS buy-in because of the kind of scale of this thing. I don't think it could be done by kind of a private company or charity, but the pilot study is probably needed to convince them that it's worth doing. And I think there are some miscellaneous questions about kind of cost. So current proposals are very, very early stage, very, very rough cost estimates. You would obviously need a more specific cost estimate, and looking at other sequencing technologies like nanopore. On the theoretical side, I think there's modeling that can be done. If we have a disease at a given prevalence, how likely are we to detect it with all the methods I've just gone through? What level of surveillance do we actually require? And also random sampling is a method I haven't touched on, but in theory, you could just take random samples from the population, roughly comparable to wastewater in how it would be useful, and metagenomics, because you could detect anything, because we're not just looking at symptomatic or animal cases. And because we're not doing it from wastewater, it's going to be less dilute. We might avoid some of the issues with read depth, the amount of sequencing required. And also, obviously, the question I mentioned earlier, what do we do after detection? Once we detected a potentially pandemic-causing pathogen, how do we then avoid a pandemic? I think this is a question for epidemiologists, vaccinologists, public health people, policymakers. All angles need to come in to answer this question. And then predicting pathogenicity, how do we go from sequence data to information about transmissibility, fatality, that kind of thing. Just to finish off, I want to give kind of a few reasons why I'm quite hopeful about this, but I think it can be done. Cost of sequencing is dropping really, really rapidly. There are also some quite major patents expiring in 2024, which will hopefully mean it drops even more. The cheaper it is, the more feasible it is. New methods for kind of doing the surveillance are continually being developed, especially on the kind of computational side, analyzing sequence data, that kind of thing, the metagenomics, better methods for that, all being developed. And also attention's growing. Largely as a result of COVID, you've got individual researchers, policymakers, biodefense people, all genuinely seem to be interested in making this kind of thing happen. Thank you very much. I hope I didn't go over time too much.
Awesome. Thank you, Jacob. Cool. We'll jump into some questions. So Hayden mentioned that when your slide is showing all of the different number of samples that you were required, and maybe you can jump back to the slide, it showed that the farm sampling was the largest source of sampling. And Hayden asks, yeah, are zoonotic transfers on the UK farms among the biggest threats, or do you think there are other threats that we should be more concerned about potentially?
That's a very good question. There have been quite a few studies looking at kind of where are zoonotic diseases likely to emerge. In the UK was quite high risk for emergence of a new disease because we have quite intensive farming, quite dense populations, quite near to farms, various reasons like that. However, having said that, there is still a bigger chance than not that it would arise from somewhere else, anywhere else in the world, and be imported, which is why something like the environmental surveillance of ports of entry helps to kind of tackle that. And yeah, 12,000 samples a week is quite a lot for a relatively small chance at arising here. But we do have the elevated risk. So whether it's worth it, I think is up to debate.
Kevin comments that sequencing Heathrow wastewater alone seems like it would be the most efficient. Yeah, does anyone have any more comments? Feel free to unmute yourselves if you have questions, or raise your hand.
Mainly that I would just like to say I would love to see the UK do something in this area, because here in the US we have this issue that you have to actually get something through Congress. And although something like Nucleic Acid Observatory is actually in the 30 billion budget request. It looks like Congress is cutting all pandemic preparedness funding, even though we're spending something obscene like 4.7 trillion on the budget and infrastructure. So we may not get anything, but it's also worth noting that deterrence is a huge factor here. Just someone needs to do something like wastewater sampling and make it known that they are in their major airports. And then that itself is a deterrence against all subtle engineered biological weapons.
I think that is actually a very good point on deterrence, and that even if we can't detect things very easily, the fact that people think we might be able to would probably be a big benefit.
A question from Abe. How concerned are you that if we got this mass sequence information, we'd actually be able to draw any insights on pathogenicity from it at all? So yeah, my understanding of this is can we potentially draw any pathogenicity at all? Or is this something we just like, is impossible to do at something?
That is probably what I would say the largest concern I have, and probably the biggest barrier to actually implementing this well. It is really difficult to go from sequence data to pathogenicity. It is doable to some extent, as far as I'm aware. I think especially with better computational models and that kind of thing, especially as kind of structural biology improves. I think it can be done. It is definitely improving quickly, but I would say it's currently probably the largest barrier.
Yeah, I think with the advancements in DeepMind and AlphaFold and stuff like that, then that would be really sort of go hand in hand. Very cool.
Yeah, agree.
And so just for the recording's sake, so we have Hayden expressing some excitement about running a pilot, and Kevin commenting that Predict is a major source of information hazard. So important to keep this in mind. Beautiful, cool. Thank you, Jacob. We will now move on to MacGregor's talk. I shall make MacGregor a co-host.
Hi. Yeah, it seems like you can't. It seems like you can't see me. I'm not sure why.
Would it be easy for you to leave the Zoom room and rejoin?
Yeah, I can do that. Yeah.
The classic switch it off and on. The engineer's solution to all global problems. Does anyone have any questions? Any other questions for Jacob while MacGregor is sorting things out?
Same issue, unfortunately.
Don't worry. We'll visualize what you look like, and we'll just appreciate your slides.
Okay.
So I'll make you a co-host, and feel free to start sharing your screen.
Great.
So for context today, MacGregor will be talking about government communication of risk in future pandemic emergencies, an existential risk perspective.
Great. Okay. So hi everyone. As Dewey said, I'm MacGregor, and I'm going to be sharing my work on how to communicate uncertainties in the context of pandemic emergencies. Communication as a whole is a vital aspect of managing any sort of societal risk, like a pandemic outbreak, and it's vital because it allows a link to be drawn between the expert understanding of the pandemics and the publics who can then benefit from that knowledge. And it gives authorities the power to coordinate the public's behavior in appropriate ways so that there could be an accumulated effect, which is beneficial in avoiding the risks. Now, in pandemics, this means you need the publics to understand like the complex dynamics of the disease and the health implications. You need their behaviors in terms of things like social distancing, lockdown, testing, to widely adhere to the correct things in those areas. And you need them to maintain continued trust in the authorities so that future communications, whether they're either later in that pandemic or in future pandemics and future risks, are also kind of listened to and taken on board. So just checking, I've got a load of Zoom stuff in front of my slides. Can everyone else see the slides clearly?
Slides are looking perfectly.
Great. It's just mine where there's something, but that's fine. Okay, so where's the uncertainty coming from in a pandemic? Well, like any knowledge about anything is uncertain, and that's an issue for communication. But like in pandemics, it's essential that mitigation measures are implemented like as early as possible, and that means you're going to be acting on uncertain information. Like you need to make decisions before you have all the information. You've also got like huge amounts of data. You've got the messy public health context, and you've got intrinsic uncertainties associated with epidemiological modeling and making predictions about the future. And of course, you also have this existential risk aspect, which is just another uncertainty, but the magnitude of the probabilities and the magnitude of the harms is so different from those more sort of everyday risks that actually our intuitions and our ways of communicating that we use in everyday life, they don't actually they run into issues when we start trying to talk about like the very small probability but very high harm risks. So that brings us to this central problem of uncertainty communication. So authorities are faced with a choice. They can either communicate uncertainty about their social distancing measures, which runs the risk that the public see this authority being uncertain and think, well, they don't know what they're doing. I'm not really going to trust them. I'm not really going to feel that what they're telling to me is credible, given they've just admitted to me that they're not completely sure if it's the right thing to do. This is going to make them slow to respond with the advised behaviors, and that's like seriously problematic when like a disease can spread a long time. Like a disease can spread a problematic distance like in 2 days if people don't lock down quick enough. The alternative is not to mention the uncertainty, and that's going to make people comply with your instructions much better in the short term. But if the policy turns out to be wrong, which is like always, like even if you're perfect, that's going to happen given your evidence is uncertain, then you're going to have this catastrophic loss of trust. And that's really difficult to recover once it happens. And it's just going to completely undermine any future attempts at communication. So that's the key thing I'm trying to address here. So the way I do that is to explore beyond the simple statement of uncertainty. What other things can we add to those uncertainty messages so that we can achieve our goals of communication in terms of like the belief, the trust, and the behaviors that people are engaging in? Okay, so what does the existing research look like? Well, so there's limited research on like the specific communication of uncertainties in emergencies. And this tends to be very focused on specific use cases such as seismic risk or environmental pollution. And those two literatures don't talk to each other. They pretend that they're dealing with separate issues, despite the fact that the ideas are very related. And there's not any sort of generalization of those findings. Other research is less directly relevant, but can help in this area. So like psychological literatures explore how we understand isolated uncertainty statements, and behavioral economics looks at how people make decisions on these bases. Like I think if thinking fast and slow is a thing that people have probably some people might have read, that's the sort of idea we're talking about, like how if you're given different odds on different bets, how do people make those bets? And the more directly applicable to the pandemic case is the crisis and emergency communication literature, which is it's towards the grey end of the literature, and this is kind of practitioners giving their experiential advice on how to deal with emergency situations, and with like kind of limited commentary on specifically uncertainty communication, but there's no real discussion of like empirical evidence of how message content and uncertainty affects the outcomes of communication. Okay, so sorry, I've lost my place slightly. Okay, yeah, so I collated findings from these literatures, and I've used it to build a minimal anatomy of uncertainty messages. Then I moved on to make recommendations about how uncertainty messages should be constructed, and identified areas for future research. So this is that minimal anatomy. These are all the different factors I think you could possibly include in a message about uncertainty. Now, the first one is that simple statement of uncertainty. So that would be things like the death rate is between 0.5 and 2%. The second factor we can include is an explanation of where this uncertainty comes from. So we don't know the precise death rate because we don't have a count on the asymptomatic and mild cases. So that stopped us calculating it. Thirdly, we can include descriptions of the relevance of that uncertainty. So building on that example, therefore, the upper bound of deaths in the next 6 months is 50,000. Fourth, we can describe the rationale for any decisions that we're going to make on the basis of that uncertainty, e.g. avoiding 50,000 potential deaths is enough of a benefit to justify the costs of the lockdown we're going to enter into. And fifth, we have the option of hierarchically layering the uncertainty information by complexity. So our initial communication of 0.5 to 2% might include a hyperlink, which then goes to more detailed things like probability distributions, and you can even show the raw data once you get to that. Now, that's a very simplified overview. Every one of those elements can include additional steps, like many possible additional steps, some of which include clarification statements, which would preemptively correct misunderstandings of the original statement. Secondly, we can explicitly mention contingencies. So that's ensuring that people understand that this uncertainty means that different outcomes are possible. Third, we might acknowledge alternative points of view about our decision, which would help people sort of trust that we have considered those alternatives. We're not just like blinded in our pursuit of our decisions. Let's have a look now at actually what these sort of uncertainty messages look like in the wild. Now, hopefully this is going to work. Can people hear that?
Nope.
It seems like people can't. Okay. Okay, that's going to be problematic. Okay.
If you click on the video link, you can just watch it on YouTube as opposed to on the slide. And okay. I would maybe that'll work. I'm not actually sure that'll work. But we can try in case it's something to do with the slides as opposed to the.
Yeah. It seems like people still can't hear. We still can't hear?
Nope.
No, okay. So we can power through.
Lara suggests go to the drop down on the slide menu and click Share Computer Sound.
Mm-hmm. Is that here?
Yeah, I'm not sure where it is. 3 dots on the top. Oh,
Here we go. Here we go.
Beautiful.
Here we go.
Teamwork makes the dream.
Okay. Okay, so I'm going to have to wind back a little bit.
Professor McLean will explain the science. The government position, the UK government position hasn't changed, not least because the most important thing people can do is the social distancing, as opposed to the weak science on face masks. There is very clear science on social distancing and the importance of it. So that is our absolute priority in terms of the message to the public. That the social distancing, staying at home, is the thing that is helping to save lives by flattening the curve. That is the #1 thing. Professor.
The recommendation from SAGE is completely clear, which is that there is weak evidence of a small effect in which a face mask can prevent a source of infection going from somebody who is infected to the people around them. Now, of course, under our current circumstances, anybody who has symptoms really must stay at home, and that's the thing that people have done so brilliantly. But we are also concerned that some people are infected who don't have symptoms, or maybe don't have symptoms yet. And that is the reason that SAGE has put so much effort into looking at this question. But the answer is clear.
Okay, so we missed the end there, but I can make my points. The first thing I want to draw attention to is this phrase weak science, which both the speakers use there. The issue here is that Hancock uses that in a way that it would allow people to interpretation that weak should lead people to infer that masks don't work. And this was then backed up when he kind of like moved quickly on to saying that like social distancing is the better option, and it kind of like pushes masks down to the side, which is problematic given that in the future, the government then was like, well, no, actually masks are part of our policy. Now, ways in which this could have been improved, this could have been avoided, would be to explicitly clarify that like, no, masks do have a small benefit. There could also have been acknowledgement of the contingency that like, well, we're not sure at the moment, but like we might require masks in the future. It would have been also easy to just refer people to a source of extra information where they could go and learn about masks and the evidence behind them. The statement from the scientific advisor after Hancock was also interesting. This is the verbatim quote. The answer is clear that the evidence is weak and the effect is small. Now, that's fine. Like there's no ambiguity in the wording of that sentence, but the answer is clear, refers to a very specific question. What is the evidence on masks? But it'll be very easy to interpret if you were just casually watching that on the news, that the answer is clear was about the question, would a mask protect me from COVID? Which the rest of the sentence would then imply that like perhaps it wouldn't, and that just wasn't the case. So that's when it becomes very important that it's very explicitly labeled which uncertainties are being talked about, because there are an infinite number of uncertainties in any situation. And yeah, so that's one of the key things that needs to happen. I'm aware that I'm infringing a lot of my time, so I will quickly move along to the further directions of work. And now, so the important thing to realize is that the things I've presented here are intuitive and things which seem like reasonable ideas of ways to improve communication. What needs to be done is like some rigorous and strict like empirical testing of what kinds of messages about uncertainty actually lead to beneficial results, like when they're used in their specific context. And an important part of that is realizing that like there's no good message, right? There's the best message in its context. And so that means in an emergency situation, you're going to need to be able to rapidly develop and test messaging, and someone needs to work out like how that should be done. And yes, thanks very much for listening, and I will look forward to your questions.
Excellent, thank you, MacGregor. So there's been a thriving discussion in the chat, and Sean asks, how much does this vary culturally? And he was he was struck by the different communication approaches in UK government messaging versus Irish government messaging. Two fairly similar countries socioeconomically, but a bit different culturally. And the UK struck him as going more for certainty, confidence, and assurance, while the Irish messaging included more uncertainty, such as "we'll level with you, but quite worried." But Sean commented that he feels like these two communication styles fit the two societies fairly well. So what are your thoughts on how much these types of communications should differ between different cultures and what the approach should be here?
Yeah. So yeah, like definitely, like you one of the first things that you're going to come across in reading about like norms of communication is like you need to fit your communication to your audience. In terms of the difference between the UK and Ireland of like being certain versus uncertain, versus admitting your uncertainty, the intuition of people in power is that they should be certain because that makes them look credible, but it's just such a short-term reward, and like anyone who wants to maintain credibility over any sort of distance of time needs to be honest. They need to show people genuinely what's what, and a key thing was over reassurance. Over reassurance is one of the best ways to cause panic. And people don't want to hear everything's fine. They want to hear, we know you're scared, we are too. Here are all the sensible things we're doing about it. Here are the things you can do about it. But that's more of a point about communication in general.
Yeah, any other questions from the audience? Feel free to just unmute yourselves or raise your hand via the fancy reactions feature. Maybe a question for myself. Do you think there is a role for more people to try to go into policymaking or politics with the intention of improving risk communications among leading politicians? Like, do you think this would like be a particularly good way to try and mitigate future pandemics? To actually just go into government and like try and see how we can like integrate these types of principles within the government, or like create a culture in which risk communication is like taken seriously. I have like no context personally on like whether this is a thing that's already happening, but just a thought. Yeah,
I mean, so it more generally than like the communication of risks, just like the way that people understand risks creates so many issues in the intersection of like publics and politics and science, because everyone understands what a risk is differently. So I think to like any important decision you're making is about risk, right? It can be framed in that way, and so I think understanding how to be able to like explain those situations to people better, like is at every step of that process, from individuals in society to policymakers via scientists and expertise. Like each link in that chain can be improved by better understandings of how to communicate risk. And that then affects every area in which risk is a factor, which is most areas that we care about. So yeah, like it seems like a really important thing. And like the thing I would say is like the the bottleneck is not our understanding of risk. Our bottleneck is our ability to implement that and get structures, like get policy and decision-making structures made so that they're able to deal with risk appropriately. Looking through I watched a lot of hours of press conferences, and it's just like, I can sit there and just like every 1 minute of footage, I can be like, look, you just done this so wrong. Like, don't need to apply any of my research. I just need to apply like the first paper that I read. And it's just like, you're just not doing the most basic things. And I think that generalizes across all of the ways in which people deal with risks. Yeah.
Go for it, Sean.
Thanks for a fascinating presentation. I wanted to follow up by asking your thoughts on the role of narratives in communication like this. So there's communication around risk, and there's also sort of narratives around risk. So the UK, I felt, had a fairly strong narrative where it kind of like, I don't know, built on like World War II spirit of we're all in this together, support our NHS kind of community. And I think the role of narrative is going to become even more important when it comes to like, how do we learn from this risk? Like, what is our narrative going forward so that we, prevent the next pandemic, so that we come away kind of stronger and better prepared? I know that that's a pretty broad question, but do you have a sense for like, that side of things, not just like communicating the information, but sort of telling the story that kind of motivates people going forwards?
Yeah, so I agree that that's very important, and I think that's the thing that I've hit on is like, just like raw numbers don't help, right? There needs to be something, and what you need to have is a narrative which unambiguously matches what the numbers tell you, so that for some people the narrative's enough, and then there's the people who look into it in more depth, and it's like, oh, good, the numbers match with the intuition that the narrative was giving me. And I think the key thing to bear in mind, especially in the risk context of narratives, is like, what you're doing there is you're almost making a comparison, an analogy. And it's really important that when you do that, that the analogy is a close enough of a match to the thing that you're describing that people don't feel that you are either sensationalizing it or trivializing it. And I think, with the World War, it's like, well, okay, like those, in terms of the societal response, like those two things are probably the same order of magnitude. So that was like probably appropriate. But if you started using the World War narrative to motivate people to recycle, right, where it's like, that is also we're all in this together sort of thing. It's like, well, no, you're just kind of like, you're just kind of abusing our emotions here and like trying to like overhype us to do something that doesn't really justify that level of emotion. And I think that would be an important thing to bear in mind.
Excellent, thank you. Cool. All right, let us depart for a break now. So you can either chill out until 5 to 8 p.m. BST, so around 20 minutes, or you can join the Galaton that I've popped into the chat if you want to socialize and discuss with other participants and the audience who are in the other Zoom. Otherwise, I shall pause the recording here and we'll return in 18 minutes for Oğuz's presentation on bioweapons. So yeah, thank you all and see you in a moment. Beautiful. Can I get a thumbs up from people if you've returned? Especially those with without the video feeds. See some thumbs. Beautiful. Cool. Let us begin again. I hope you all had a nice break, and I shall now make Who's a co-host? Awesome. So Oğuz will now be talking about the political feasibility and the future of biological weapons, lessons from the COVID-19 pandemic. So over to you, Oğuz.
So thank you, Dewi. Also thank you for everyone that so far has presented their work. I try to keep up with the quality, hopefully. So as the title says, my presentation is mostly political, about the feasibility in a political side, and if the weapons are feasible, what would happen in the future, what we might expect. So without going into detail, I would like to talk more about why should we care about biological weapons? Well, the thing is that even the traditional biological weapons were really risky. They were quite hard to detect because you cannot really see a biological agent. Also, they are easy to produce, store, and deliver relative to the other weapons of mass destruction. Namely, nuclear, as you know, is quite hard. You can even spot them. Chemical, relatively easier, but still you need some specific facilities. In comparison to them, there it was more easier. The one problem it had was it was quite uncontrollable, even for those who are using it. Also, they are quite indiscriminate in killing both civilians and military, but also allied and rivals. So that was the only one of the only obstacles that it had. What with synthetic biology, it's getting more feasible in the technical part. First of all, synthetic biology provides easier genetic modification in all sense. Access to synthetic biology is getting easier and cheaper. Also, we might expect custom-made weapons in the future because of the opportunities that synthetic biology provides. So against something new, it might be harder to defend against. Also, it might give more control for the attacker as they're engineering a pathogen. Sorry. And as we have seen with the COVID-19 pandemic, that we did not have really much sufficient preparations, even for a natural one, let alone an engineered one. Therefore, I asked 2 research questions in the first part of my presentation. I'll answer my first part, namely, is an advanced biological weapons attack currently feasible in the current political and technical sense? And if so, how would actors behave in such an environment? For the second part, it was more of a second part, I tried to utilize scenario planning in order to see those behaviors in a more realistic setting. I couldn't do more of an research based on empirical data like specific biological weapons use this because there were really few that are confirmed. Also, we're talking about a highly unknown future, and the weapons that we have will be probably unlike traditional biological weapons. Therefore, I tried to use COVID-19 experiences as a substitute, which I will later talk about why we can use them. So I think that chart kind of proves my point. It's a nice little summary. I tried to make some outlines of what are the possible behaviors and feasibilities. Then I'll add up more details with empirical data and I create scenario. So about the feasibility of the biological weapons, the biological weapons themselves mostly favor offense. They are, if we base it on cost balance, by that I mean it's cheaper to attack with biological weapons and be successful than defend against them. Also, they are dual use and difficult to find any evidence. So by that I mean you can easily have a civilian complex. So you can take a civilian complex's capabilities and easily modify them to produce bioweapons. It also requires tacit knowledge, mostly in the institutions. So that's a barrier to get biological weapons. Also, it requires, at least for the states, positive expert opinion. By that, I mostly mean it is usually the experts that pitch the idea that biological weapons can be something useful. So it also requires this to convince the policymakers. In addition to those, it requires high degrees of planning and integration to a long-term strategy to make sure that it works. When we think about these and materials, the required material superiority to produce these weapons, great powers or regional powers seem to be the most capable actors, but that does not mean that it will go on in this way. In the future, if the technology democratizes enough, we might have a future threat from non-state actors that we should not ignore. But in this presentation, I'll mostly focus on states. So then after talking about this, I thought about what would be an attack look like. I decided on a covert peaceful attack for disruption. Why is that, you might say? Because usually covert attacks are cheaper. You don't have to mobilize military, you don't have to do much. You just have a specific team working on the issue. Also, it means no audience or normative costs. By that, I mean you cannot, if you're in a democracy or an authoritarian regime, there's not really much backlash going on. Also, no normative cost, meaning that the things that are associated with biological weapons are not there. It is, some issues cannot be approached by direct military action in these days. By that, I mean mostly because of the alliance law, so the overall norms against war. In addition to that, interstate wars are rare, so automatically it's more like that we might see something like that in peacetime. Also, for that reason, I think forcing a rival for lockdown is the way that probably attacker would go. Also, we have relatively weaker institutions. By that, I mean Biological Weapons Convention and United Nations Secretary General mechanisms. They had some successes. Biological Weapons Convention was the first treaty to ban entire class of biological weapons. I think that's a great success. Also, there were fewer cases of biological weapons use. I think that's also a great success. But they sometimes might have problems with the government. The governments might not wish to work with them. They mostly rely on goodwill of the governments when they do a research. Also, a special biological weapons convention is outdated and quite underfunded. So we might expect some public unrest and weakening of state capabilities in such an attack. By that, I conclude that it's quite feasible. My first question is a solid positive. So moving on to my second question, how would such an attack would look like? I return to the experiences of COVID-19 pandemic. Why did I choose COVID-19 pandemic? It can be a question that you might ask. I believe because, first of all, natural outbreaks are really hard to differentiate from artificial ones. So the effects are quite similar on the public, so we might, on the policymaking, so we might expect not much of a difference. It was quite novel for decision makers because the virus is quite new. It caused disruption and also fits to the definition that I thought of a pathogen, which probably will cause low casualties and medium spread. So probably the states would like to have no pandemics or international epidemics in order to control the spread of the virus pathogen that they are using. Also, we have immense amount of empirical evidence with COVID-19 pandemic, so it's easier to use. Also, it's realistic and memorable for all of us. So what are the empirical data that some are used? So yeah, I tried to look at investigations by World Health Organization and private researchers, but that remained mostly inconclusive, and we might expect similar thing happening with biological weapons. And even though there was strong screw towards zoonosis, namely spread from an animal to human, also they had some difficulty with cooperating with governments. So sorry, I missed a slide in there. Also, probably the defending part will most likely to follow a policy that try to limit meetings below 100. This might change to government. Also, they might close the non-essential businesses or education if the population is younger. Also, this might reduce casualties or pressure on infrastructure, especially healthcare, we might expect, but it might cause an economic downturn, which precisely an attacker would aim for. Also, it might cause public non-compliance and protests. We have seen with the COVID-19 pandemic some political effects of the whole pandemic and discontent increasing day by day. And we had some online dimension, which we have seen spread of misinformation rapidly. So my scenario is pretty simple. As great power attacks an ally of a great power, they use a super spreader to spread the virus. Then after that, 3 cases increase and 3 scenarios follow. My first scenario was, I call it undetected virus. By that, I mean the virus is not detected as an engineered virus, so it remains, the whole thing is not as a natural pandemic, natural epidemic. So in that case, state B, the attacker faces no repercussions, and state D is, attacked one is highly damaged. In the scenario of a detected virus, by that I must mean if the virus is detected before it can go very far, we might expect less damage on the attacked state, more damage on the attacking state, because it turns out that they have used a biological weapon, which is highly shunned upon in the international community. So probably attacking state will be more likely to use. Also, I had an exposed virus scenario, which I include, which there are some suggestions that the virus can be artificial, but there isn't really much evidence that they can work on. In that case, both of the parties lose to some extent, and also they might cause an escalatory behavior in the future and go after one another and cause tensions in the international arena. So you might think that, well, states do not try to follow a pandemic, then what's the point? It's not really an existential risk. So I think there are two parts that might cause an existential risk, direct and indirect, and I'll try to talk about them in my two categories, namely flawed rationality and long-term outcomes. By flawed rationality, I mean that the states might not have the best rationality when doing these decisions, as I put in a scenario. They might have imperfect information. One of the examples can be that they might use a pathogen that they deemed to be safe, but in reality, it was a real dangerous one and might easily cause a pandemic that might eliminate the humankind. Also, there might be accidents or leaks from these laboratories, and it's not really uncommon to see accidents or leaks. And not necessarily the main product, but a byproduct can be released in nature, which might also cause an existential risk towards humanity. And also, even though, let's say that this virus has low spread rates and low casualties, let's say, if it spreads long enough and as expected, the states might not react in time, it might even grow out to be a pandemic. So in that case, we can't really trust one's rationality. But on the other hand, we have some long-term outcomes that we might expect if the rationality works perfectly. So in that case, we might expect security dilemma or proliferation of biological weapons. And in that case, it might be a problem because even though one biological weapon is not risky, 100 or 1,000 one might be and cause human eradication used by different states. Also, let's say that biological weapons did not do anything. It still causes escalatory behavior, which causes higher risk of war, which is a risk factor. Also, there might be different rationales of the states. Let's say that a state has biological weapons producing capabilities, but the state was hijacked by a cult or a religious group, which they aim to eliminate the whole humanity, let's say, or some idea like that. Because they have such a different rationality, they might cause an existential risk easily. So what are my suggestions to eliminate those? I've mostly focused on tipping on offense-defense balance. By that, I mean making defense less costlier and offense more costlier. So how can we do that? Well, for example, mRNA vaccines is an example. It's if we can either roll out vaccines in a rapid rate, we might eliminate the disease. And if that's so, it reduces the cost of defense. Also, these technologies are getting cheaper as well. We might also try to have better surveillance and forensics. I've not really touched upon the genomics part because Jacob has already mentioned them. But also, we might think of use of social media data to locate outbreaks before they become something riskier. In addition, we might think of more authoritative institutions. By that, I mean giving more authority towards Biological Weapons Convention and also United Nations Secretary General's mechanism. The problem with it is that it might sound too utopian and the states might not agree on that. Instead, I would say that maybe it's better to focus on alliances of willing rather than having this global initiative. And we have already examples like the Australia group for a simpler one. We can also prevent them by norm building, which would also increase the cost of attack. Also might dissuade some of the experts from proposing such biological weapons in the first place. If we cannot prevent them, at least having quick and resilient measures would lessen the damage of an attack. And if we can jump from one normal to another normal in a really quick manner, then the economic costs and most of the costs we associate with any sort of outbreak will be lesser. And we can also think more about the memories of the COVID-19 and focus on what else can we do, focusing on this empirical data. I just scratched the surface with this research. So that's all for my part. I would like to thank my mentor, also CERI team for organizing this event and also helping us throughout the way, fellows for their most valuable feedback and for this 8 weeks, also EA Cambridge for their contribution in every part to make this research possible. If you have any questions or need any sort of clarification, I would be more than happy to answer.
Excellent, thank you. Yes, if anyone has any questions, please feel free to unmute and ask away or raise your hand. Yeah. Here we go. Jacob has asked in the chat, are you concerned about the dual use nature of some defense technologies, either as an accidental outcome, such as from information hazards, or from states pursuing offense under the guise of defense?
Well, thank you. That's a great question, because that's also one of the criticisms of evaluating the feasibility, political feasibility through offense and defense. The thing is that you cannot really put a technology in the category of offense and defense, because usually you can use them for both. But on the other hand, I think that some of the technologies have obvious one-way uses. Maybe to give an example, if let's say that we find a method to produce vaccines rapidly, it reduces the cost of defense, but that doesn't not necessarily cause any offensive effects. And the one other thing that you said about states pursuing offense under the guise of defense, that's also another concern. None of the states today have an offensive program, and in the future, if an attack happens, probably most of the states will claim that they just have a defensive program. So that's another problem that we cannot really solve unless we have some sort of transparency, which I see highly, it's quite impossible for now, I think. But yeah, I have this concern about it. But I think that as the history has shown with other examples, we sometimes have a clear distinction between one or two with a technology.
Any other questions? Well, maybe a question from myself. What has been your biggest updates in terms of your perception of risk after having done this research? Are you more concerned now about state bioweapons programs or less concerned? And if you are, then what specifically has caused you to update in that direction?
So to this question, I would probably answer both. I know a really neutral answer, but I think on the one hand, I have seen that it is harder to pursue biological weapons than we make them out to be. It requires a lot of organization to be done, and also you need to think about other stuff as it is worth to use it, or what will be the real costs. If you think about it, and also some of the norms related to them, it seems like they have lesser probabilities. But on the other hand, when we think about the whole advance of technology and these rapid advancements, it's harder to not to get scared about the future of biological weapons. So I think through my research, I have realized that it's not as easy as to use biological weapons. There is a lot of complicated requirements that go in there, but also making them more feasible does not help us right now.
Okay, thank you very much. Excellent. Yeah, if there are no more questions, doesn't look like it, we shall jump to Suraj, who will be presenting on, let me get the title, Preventing Engineered Pandemics, Insights from Present-Day Synthetic Biology Policy. I shall make you a co-host, so you should be able to share screen. Take it away.
Yeah, so hello everyone. My name is Suraj. I am an undergraduate at Brown University. And this is my project for the 2021 CERI Summer Fellowship, Insights from Present-Day Synthetic Biopolicy. So just an outline of the presentation. I will begin with some of the motivation for why I pursued this project, follow up with some methodology and how I went about assessing these different policies. And then I'll get into one example of the policy analysis that I conducted, followed by some alternative approaches rather than just, policy after policy, what else can we do to mitigate risk in synthetic bio? And then I'll conclude with a scenario of some of the emerging threats that might need to be considered with synthetic biopolicy, and particularly in the field of cyber biosecurity, which is a new and sort of neglected field. So my motivation for pursuing this project was this field of synthetic biology has become extremely democratized, right? It is so easy for someone to synthesize a pathogen today, and it has become so widespread that even at these different biohackathons, even high schoolers and undergraduates can, use these synthetic bio kits and create their own synthetic biology. And although that is great for the progress of research, at the same time that poses new existential threats in that we have less oversight over how widespread the synthetic bio is. And some of the overlooked steps in this process, one is DNA screening. So DNA screening is taking the sequence of DNA and comparing it to known harmful sequences. And so this term of screening is not all that is done in terms of synthetic bio. That's not the only thing that we can do to make sure that a pathogen is safe. The second thing that we can do is assess customer intent, making sure that the customer who is ordering a synthetic pathogen actually uses it for what they say they will. We like to believe that most synthetic bio researchers do have good intent, and that does happen to be the case. But there are a few with malicious intent, which can, pose an existential threat on their own. And then there are also those customers with good intent who make careless mistakes. And so that poses another gap in this synthetic bio pipeline that could lead to an engineered pandemic. The last major overlooked step is an information hazard. So we have mentioned information hazards previously. It is a piece of information that is disseminated that can cause harm or enable someone to cause harm. And an example of this information hazard in synthetic bio is this paper that was recently published that I was reading. They actually published a step-by-step process of synthesizing COVID-19 in a highly transmissible form. So that can, you can see on your own why that might be harmful, because someone with malicious intent can now has the access to synthesize COVID-19 and release it out in the world. And so that is definitely a source of existential threat in the field of synthetic bio. And lastly, DNA providers today, they are economically incentivized to make DNA as accessible as possible, because we do want scientific research to progress. But at the same time, they are de-incentivized to properly make sure that the pathogens they release are safe. And that comparative cost is what leads to this existential threat, in that the providers don't have the incentives to make sure that their DNA is safe. So an overview of my project and what I did. I took 4 prominent present-day synthetic bio guidelines. 2 of these were synthetic bio policies that are already in place, and the other 2 were proposals for future synthetic bio policy. And the way I selected these policies was from expert recommendation, particularly my mentor, who is a very prominent biosecurity expert and gave me these policies to read. And I analyzed them for strengths and weaknesses from a GCBR mitigation perspective. The 2 criteria that I mainly used when I was going through the policy to determine whether a recommendation counts as a strength or a weakness was how neglected is it in the other policies, how little is it mentioned throughout all the different policies and proposals that are out there in synthetic bio, and then how feasible is it to respond to this problem, or how feasible is it to carry out this recommendation. And both of these criteria sort of helped me in investigating the emerging technological threats in synthetic bio, because it pointed to the different gaps in the policies that exist. So this is the results of my policy analysis that I have included in my deliverable. Obviously, there's not enough time to go through each policy and strengths and weaknesses, but I just want to give you a flavor of how I sort of did that. And I will be using the G20 Agenda for Sustainable Development as an example. So this is a biosecurity agenda that was proposed by the G20 consortium, which is a group of the 20 most powerful nations in the world. And the way that policy advisors sort of look at this agenda is they look to this agenda for recommendations on how to carry out their particular country's biosecurity policy. And so getting into some of the strengths of this policy was One was do-it-yourself synthetic bio. This proposal, this agenda mentions do-it-yourself synthetic bio as an emerging threat in this field of synthetic biology. And that is because people who don't have knowledge of this field are using synthetic bio kits, like I mentioned earlier. And that makes us more vulnerable to certain attacks because we are unable to keep track of all the synthetic bio that is out there. And a response to this is Germany actually, one example is Germany has an act sort of outlawing synthetic bio practices outside of research organizations and academic institutions. And that prevents sort of these unknown attacks, at least in terms of policy. Another potential strength of this proposal was the mention of a labeling system. So the mention of the importance of the labeling system. The material safety data sheet for harmful chemicals is an example of what we have right now in labs that are not related to synthetic bio. And I don't see why we don't have this type of standardized labeling system for synthetic bio. So what happens right now is synthetic DNA providers sort of ship their DNA off and they have sort of a basic safety data sheet, but this data sheet is not standardized, right? It doesn't include necessarily all the information about precautions we need to take when handling synthetic pathogen, as well as the accountability and the manufacturer of the DNA. And so moving on to the weaknesses of this policy, one weakness that I found was that it is extremely top-down. And by that, I mean, it is up to the discretion of the member nations to implement these recommendations. And so it doesn't have as much power as it initially would have if it was a unified consortium such as the IGSC in making sure that DNA providers follow synthetic bio guidelines. And so all this policy analysis, I'd like to mention that policy after policy may not be the best way to sort of going about mitigating threats related to engineered pandemics. And so if policy after policy is not the best way to go about doing this, then what is? One alternative is a bottom-up approach where we educate researchers, postdocs, undergrads, to sort of have this existential risk mindset in synthetic bio. I'm not saying that they need to necessarily know about existential risks, but just being cognizant of the education that is available in synthetic bio. Right now, an undergraduate can sort of get into a biolab just by completing a few trainings that require very few rigorous educational skills. And so somebody who is in a lab may not necessarily have the requisite knowledge for making sure that their DNA is safe. And that is a very important approach that I think warrants some further consideration in terms of alternatives to policy-oriented approaches. And lastly, to sort of conclude, I'd like to present a scenario related to this field of cyber biosecurity. So this field is very neglected in that it is the intersection of cybersecurity and biosecurity, but there are very few experts who have expertise in both of these fields. And the reason I'd like to mention this is that this could be an example of the emerging technological threats that might need to be covered in future synthetic biopolicy. So just to make these threats clear, I'll present this scenario. So consider Alice, who is a researcher at an academic institution who wants to synthesize some DNA. She goes to Bob, a DNA provider, and in a low-risk situation, she would ask Bob for her DNA. Bob would screen it to make sure that it's safe based on his company's protocols, and represented by the black line, he would send that pathogen back to Alice, who can use her DNA for her experiment. Now let's consider a higher risk scenario. So Eve is a hacker who has infected Alice's computer with some malware. So now what Eve can do is, before Alice sends the sequence information to Bob to synthesize, Eve can actually use this technique called DNA obfuscation, which is disguising the DNA, and she can send that disguised sequence over to Bob. So what happens is, in reality, Eve has malicious intent and Eve has replaced the sequence that Alice wanted with a harmful sequence, but Bob does not recognize it because of gaps in the current screening protocols. And so this obfuscation, which is related to a cyber hacking technique called code obfuscation, this obfuscation makes Bob unaware of this harmful sequence that he is synthesizing. So Bob would synthesize the harmful sequence, and then he would send it over back to Alice, represented by the red arrows. Now, Alice can also additionally try to check to see if the sequence is harmful, but Alice's check will be fruitless because Eve has already infected her computer. And this scenario is just not a scenario. It is actually a reality that researchers have sort of proven that there are gaps in the IGSC's harmonized protocols, the screening mechanisms that exist today. Researchers have shown that such a cyber attack, such a cyber biosecurity attack would be possible. And so this just points to something that we need to consider when implementing future policies in terms of cyber biosecurity. And with that, I'll just summarize the main takeaways for my presentation. There are many gaps in today's synthetic biopipeline, and this exponentially increases the possibility of an engineered pandemic. The current policies in place are voluntary and often inadequate in addressing the threats related to synthetic bio, and there's little incentive for DNA providers to follow safe synthetic bio practices. Future methods of combating risks in this space, whether they are policy-oriented or not, must account for the rapid development of new technologies, as well as the democratization of synthetic biomethods. And another thing I'd like to include is that in my deliverable, I sort of hope to include a synthesis of all of these strengths that I sort of found in the different policies that I analyzed. And hopefully that can be a future proposal that incorporates all these modern technologies, such as benchtop DNA synthesis, which I didn't mention, but I covered in one of the other policies. And with that, I thank you for listening, and we'll take any questions.
Awesome. Thank you, Suraj. Yeah, any questions from the audience? As always, please feel free to flying in. Jacob, take it away.
I know this wasn't actually mentioned on the presentation, but am I right in saying that you were originally planning your project on lab of origin attribution? And if so, I'd be interested in knowing kind of why you moved away from that and towards the DNA synthesis stuff. So kind of what journey did you go on?
Right. So initially, I wanted to do a genetic engineering attribution project where I find the lab of origin of a pathogen. And from the initial literature review in the first couple weeks of the fellowship, I found from consulting with experts that this field is actually more technical than something like this policy analysis would be. And then from that, I realized that like I would have to do some types of technical, computer science self-learning in order to further my interest in this field. And so I thought that for the purposes of the fellowship, it might be better to take a step back in the process and just analyze policy and get a feel of what the current world of synthetic biopolicy looks like before we even consider after the pathogen is released. So yeah.
Excellent. Lucas?
So thank you for the great presentation. I found it really thought-provoking. So my question was related with, while policy making, let's say that we have a hypothetical, let's say someone who has malicious intent. So what should we expect this person to look like? Like, what are some of the benchmarks that we expect this person to have? Like, what is his education background, or what sort of motivation that they can have? So I was wondering this.
Right. So the way that current sort of policies check for this customer intent or this particular person who has malicious intent is they require in writing, they just require sort of what you plan to do with this DNA and what types of experiments you plan to conduct. And this way of assessing customer intent is definitely vulnerable to flaws. And so what my mentor described to me was it's like finding a needle in a haystack. It's very hard to locate these types of people. And often they might look like a postdoc who is probably disgruntled with his lab, who just might want to rebel against the system or something like that, or has lack of care. And so it is very difficult to sort of find these people and assess their intent. And it requires sort of a follow-up screening where The US guidelines currently recommend a follow-up screening where you like go to the lab and just follow up, and later on after the DNA has been sent, make sure that it is being used for what its intended use was. But yeah, there is no ideal there's no like prototype person. They're very variable, and they're very difficult to sort of find these people who have malicious intent. And so that is a gap in the current policies that only the US guidelines sort of mention, but other protocols have not mentioned or dealt with.
Awesome. MacGregor?
Yeah, so I just thought about this in an analogy to like censorship. And the thing with censorship is like, right, like, so who's going to be the censor? Like, how do you stop the mind of the of the censor being corrupted by everything they have to read? That's not worthy for everyone else. And it feels like you run into the same problem here, where someone has to be reading the sequences, right? Someone has to know what the dangerous sequences are and where they are. For example, the DNA provider, how the focus seems to be on the person synthesizing the DNA, but what if the bad actor is the DNA provider? Because although there's many fewer of them, so it's less likely, but they have much more power. They're in control of many more sequences.
Mm-hmm. Yeah, so can you, I guess, like, are you, what the question exactly was?
So the question being that it seems like the focus is on the DNA user, but like, in your experience, is that a different question? Is saying what about the DNA provider, is that a meaningfully different question, or is it just the same issues that that impact them? It would seem to me that they have to see the sequences, like they at some point have to know what the dangerous sequences are, and they are the ones who actually have the power. So it could be that they're almost more important.
Right, yeah, I think that is a different question. And I think the DNA providers, the fact that they are the current state of the system, they self-regulate and they do their own screening, and they don't necessarily have to follow these guidelines. That definitely puts them in a state of higher power than the person who's synthesizing the DNA. The only, like, I guess, caveat to that is like synthetic bio companies are sort of more concerned with profit. And so it seems that the DNA providers are more concerned with getting their DNA out than necessarily like having malicious intent. But yeah, I think, does that sort of answer your question, or do you have any like further comments?
Well, I guess that sort of emphasizes the issue, right? It's like not only is it a problem if they're bad actors, but even the like morally fairly normal actors can end up being incentivized to doing bad things. Yeah. I guess that's a lot of what you've said, right? Of like they're self-regulating, and that's not an appropriate incentive to surround them with.
Right.
Cool. Any final questions from the audience? Nice. Yeah, maybe a quick question for myself. Were there any policies that you felt like were particularly compelling, or that you would like, maybe another framing of this, like which policy would you be most favorable towards in terms of like if you were sending one document to the US or UK government to be like, this is the policy that seems most promising? Were there any of them that stood out that you felt, this covers more bases, or were they all fairly a mixed bag in terms of hitting some things but missing a bunch of other things?
Right. So I think the one that I presented, the G20 biosecurity agenda, that was the reason I presented it partly was because it pointed to the most sort of neglected problems. And I liked that it mentioned all these fields that are sort of not even considered in terms of technological threats. And so I would definitely point to the G20 biosecurity agenda as compelling. And then another one was the World Economic Forum's and the Nuclear Threat Initiative's 2020 framework for safe and secure DNA synthesis. This policy is also very compelling in that it is more of an international government system, which one of the weaknesses I mentioned was that it is international and that it has little oversight, from a top-down approach. But its strengths lie in the fact that it's bringing together experts and trying to develop this common screening mechanism that can be easy for DNA providers to implement. And so they don't have to have their own screening mechanisms. And so that policy is also, or that proposal, it's more of a proposal for a consortium. That is definitely very promising. The only thing is that in their document, they actually mentioned that by 2021, we hope to have the common screening mechanism out. And they haven't really done that yet. I guess they've been delayed by the pandemic, but it's also partly doing the work required to fulfill the proposal. And so, yeah, there are a lot of other people sort of working on this. Kevin Esfeld has a secure DNA project that is working completely independent of government right now. And he's trying to sort of have this screening type of screening mechanism. But yeah, there's definitely the two main policies that I definitely liked were the G20 and the World Economics Forums.
Awesome, thank you. And a comment that I missed from Laura on the previous discussion just for the recording. Following on from Mark, could the negligence around screening of who they sell to, these are the DNA providers, also make them bad actors? I don't know if you have any final thoughts on this, Suraj.
Yes, yeah, I definitely think that could make the DNA providers themselves bad actors. And that is one of the things that the labeling system tries to address, in that you have to include the manufacturer of the DNA and have to hold them accountable in the end for allowing this pathogen to even get to a malicious end use and being, ignorant of the fact that like customer intent is a very important part of the screening process that is overlooked. And so just checking these sequences isn't necessarily the only thing that we have to do. We have to also make sure that people are using it for the right intent. And a lot of companies fail to sort of account for this.